Hey everybody, it's Mr. N, and we are going to talk about the derivative as a function. So we're not quite to where we're using shortcuts yet. Here it is as a function, and we talked about this in the last section, so let me highlight this again. And we said that f prime is the derivative. What is the derivative? The derivative is the slope of the tangent line at a particular point. If I say at x, then it's just generalized at x. If I can actually put in a point A, and we can go at it that way. I've also said here that we changed this, added h, so that we can make this h value, that distance that A is away from B as close as possible. So we are calling that distance h, and it just makes it a little bit more general in our terms. And we had this formula, which was the definition of a derivative. Here it is, same exact thing with x. So this is the derivative as a function. That's how we present it. And again, the derivative is the slope of the tangent at x. So, knowing that, we can do some things. First of all, if we are given the graph of a function, we can graph its derivative, and vice versa. You don't know the vice versa yet. That's a little bit harder. We need to cover some more concepts on that. But for now, if you are given the function, we're going to graph the derivative. So let's take a look at this. Over here, if I have this function, and it looks like this, and I want to sketch f prime. So what we're going to do right now is called derivative sketching. So let's take a look. Since we are sketching f prime, we need to consider some things. We are looking at the slope of the tangent, and the first thing that you're going to want to do, and this one is probably the best route at doing this, is you want to find where the slopes are 0. So you want a horizontal tangent. And I'm going to graph this directly on the same grid and then show you from what I did. Okay? So this is a horizontal tangent. So that means the slope is 0. That means f prime of 1, 2, 3 in this case is 0, right? Because we know f prime of x is the slope of the tangent, and I'm telling you that that slope is 0. So what I'm doing here is I'm graphing this point, x, and the f prime of x. Okay, so at this x value 3, f prime of 3 is a horizontal tangent. So the easiest step is to always first look for these horizontal tangents. There's one right there too. That tells me that these values right here, and I'll put the points in blue, are going to cross at 0. So this is about negative. So the other one here was at negative 2. F prime of negative 2, that slope was 0, right? So that's why I put that point there. So here's what I want you to really pay attention to. I keep harping on you guys that if you can write the equation of a line, you know everything about lines. Calculus you're going to do very well in, because a lot of it deals with that. So let me draw this shape right here. And I'm going to explain this to you. Let's see if there it goes. It matched it up, so this is what I want to do with this. Look at this line. That's a 0 slope, right? That's horizontal tangent, 0 slope. As I move the line up, these are positive increasing slopes. It goes all the way up to where the slope is infinite, right? This is a really, really steep slope, steep slope, steep slope. But then these are negative slopes, and I can go lower negative values back to 0. Well, this concept may seem very simple to you, but we're going to apply this concept of how I can increase my slope and see the slope changes to this graph right here. Okay, so like look, right here, the slope goes from horizontal, and let's see if I can put this over here and show you. So the slope goes from horizontal, and notice now as I go over here, let's put this like this, horizontal, and as I go up, the slope increases right there. I've got it tangent to it right now, and it increases till about there, where this open circle you see it. right? So I will shift this whole thing here. And now what do you see happening to the slopes? The slopes start to decrease again, right? So this whole thing starts to decrease in slope. Whoop, what did I do? Okay, until you get to the top point right there, where now the slope is horizontal again. All right, so I don't know why this thing is doing what it's doing. It's flipping out on me. But then it's horizontal, and then the slopes go back negative. Okay, so that's my whole point with this. And you can see again, I'll show you, that the slope's horizontal, that's 0. Then they quickly increase. The slopes increase to about there. And this, if I were to just kind of guesstimate it, I'm just going to kind of guesstimate the slope. It looks like it's a slope of about 1. Right? So I can guess that. So the slope, I don't know for sure. I would either need to draw it out, graph it better, have some sort of equation to deal with. But it appears to be 1, because if I aim my tangent line this way, it looks like I'm going up 1 over 1, like that, right? So that's what it looks like it's aiming towards. So I'm going to say that the slope at 1, that the slope at 1, or at 0, this f prime of 0 is approximately 1. So that means I'm going to put that blue dot right here. All right? And then we said, look, from this point right here to this point right there, and let me do it with this one, from this point right here to this point right there, the slopes slowly increase. Remember, you're graphing the slope values. So these slope values, as you go from -2, then -1.5, then -1, then 0.5, -0.5, then 0. These slopes are slowly increasing all the way to a value of 1. So they increase to a value of 1. On the other side, they're decreasing to a value of 0. Because now look, again, the slopes are positive. So here's what I'm trying to say. These slopes are positive. That means your derivative graph, this is the derivative graph in blue, f prime, your derivative graph is above the axes because the slope have positive values. So my slopes are going to all be positive above the axes. But look what happens here. The slopes turn to go negative. So now I'm going to be below the axes. So this continues on below the axes. And look at on the other side. These slopes are also over here. You get to horizontal slope, but these slopes are negative also. So they slowly increase in negativity, and so they're like that. So that's what this graph is. And if you take a look down here, you'll see that I did sketch it for you. Okay? And you'll see that that's what that is. Now, here's a couple things to note. If you know the order, if it's a third order polynomial like this, I have it written down here, then the derivative will be second order. This appeared right up here to be the original, to be a third order polynomial. It appeared like that. So that means the derivative will be a second order. And notice this was a negative. This will be a negative, pointing down. All right, so that part didn't change. So if you have a fourth order, the derivative would be a third order, and so on. A second order, if you have a parabola, the derivative would be a straight line. So that's something to note. And then the domain may change, you don't know, but the range will most likely change. All right, so let's do this next example, and we are going to graph, and I'll do this down here, f of x, root x, and compare it to f prime of x. All right, so first of all, I'm showing you how I took the derivative. So what I did here is, here's my function, square root of x, and I want to take the derivative. So we know that f prime of x is a limit as h goes to 0 of, remember, f of a plus h minus f of a all over h. Well, here's f of a plus h. That's what I end up with. F of a plus h becomes square root x plus h. F of a, which is just x, becomes root x over h. Now, in order for me to find this limit, what I need to do is I need to rationalize it. And we did some of these examples. So I need to multiply the top and bottom by the conjugate. And that's what I did. So I multiplied the top and bottom by the square root of x plus h plus x, right? That's the conjugate. And then I cleaned it up right here. I foiled it out on the top. I got this. On the bottom, I just left it like this. Just leave it like this. Don't do anything crazy with it. Because the x's go away. And now look, the h's reduce out right here. Let's reduce them out for you guys right here, right? And so after you reduce out those h's, we have 1 over this. Plug in 0. This is the brute force, direct substitution. You plug in 0, you get 2 root x. So that is the derivative. So what we have here, and we can finish this on the next page now. What we have here is f of x, which was the square root of x. And here is f prime of x. I don't know if you could see that prime too well, which is 1 over 2 root x. So there's the graphs of each. Notice on this one, the domain goes from 0 to infinity, but it's closed, right? I can put in 0. On this one, it's open. So here's a situation where the domains are different, okay? The domains may be different, may be the same, but the ranges most likely will change. Now here we go. This is big time. Let's talk about other notations of f prime of x. F prime of x is the most common notation for the derivative, right? So we have f prime of x. That's the most common. Most common, but it's not always the most useful. Let's talk about these other ones. We can say y prime. So if you have y equals 3x plus 5, you can take the derivative and say y prime. That's completely okay. We can say dy over dx. This is the change in y, the differential of y over the differential of x. So the change in y over the change in x. The derivative of the function with respect to x. So this is the derivative of y, and on the bottom we say with respect. So the derivative with respect to x of f of x. d f of x, dx f of x. These are all different notations. You won't often see these two until you get to really higher level math. You'll start seeing some of these, but most likely you will see these ones right here. Okay, these ones. Now, dy dx is said, as I said it above, is the derivative of y with respect to x. This is not a ratio. I know I said the change in y over the change in x, just to tell you that it is a rate of change. It's an instantaneous rate of change, but it's not a ratio. With a little asterisk there, because sometimes we can separate the dy and the dx, and that's called separation of variables, which we'll get into in second semester. So over here we have df over dx, and that's the derivative of the function with respect to x. All of these differential operators, they indicate some sort of differentiation, and they were developed by Leibniz. And so we often call this Leibniz notation. So you'll hear me sometimes say Leibniz notation. Who is Leibniz? Well, when you hear a lot that Newton developed calculus, he sure did. He was an extremely bright man. I mean, you know everything about his accomplishments by now, and you know what Newton did, and you know how big of a scientist he was. He was an outstanding mathematician as well. The thing is his group was a bunch of scholars. He never organized everything to be nice, neat, and tidy. It was messy. His work was messy. It was very understandable. The scholars totally understood it, but he didn't develop anything as far as organize it in a manner that is going to be known by all. Whereas Leibniz came by, and he kind of piggybacked and also did a lot in calculus, but he started taking all these concepts and ideas and organizing them. So he came up with his notation. He said, okay, dy dx, that's going to be the derivative. He came up with things that were, f prime of x. He basically formalized it and organized it so that it could be published. And that was his big thing with respect to Newton. Newton didn't publish a whole lot of his stuff. He published it to scholars, but he didn't publish it to the mass public. All right. So when we say dy dx, we are saying the limit as the delta x goes to 0, right, of the change in y over the change of x. So this gives me the instantaneous. So this is instantaneous rate of change. Now, if we want it at a specific value, we can say dy dx at x equals a like this. You'll see that your calculators present it that way. All right, so now here's the next definition we're going to talk about. And this says that if a function is differentiable at a, so it's differentiable at a if f prime of a exists. Okay, so that's pretty easy concept. So if I can take the derivative at a, then it's differentiable at a. It is differentiable on any open interval a to b, okay if a or b is infinity, only if it is differentiable on every single number in that interval. If you take a look at in Stewart on page 127, example 5, he determines if the absolute value of x is differentiable. Look, when we have the absolute value of x, we have two situations. When x is positive and when x is negative, right? You solved that in algebra 1. You said the absolute value of f of x equals negative x or positive x. So you had those two situations, and that's what we have here. When x is greater than 0, when x is less than 0. That's the positive and negative version. Positive version, we end up with this. We get the limit as 1. The negative version, I take the derivative. I end up with this. So it's negative 1. So it's not differentiable at x equals 0. So it's differentiable on all reals except x equals 0. And the reason why I bring up absolute value of x, because it's going to help us with many, many things. And remember, the absolute value of x, I will remind you, looks like this. It's this v, right? So it is not differentiable right there at 0. All right, let's talk about this in depth. Okay, so here's what all of this tells us. Pause, take a breath, catch your breath, because this is super important. Here's our theorem that we're going to talk about. If f is differentiable at a, then f is continuous at a. Your author proves it on, Stewart proves it on 128, but the converse is false. Okay. If I can take the derivative, it's continuous. But that doesn't mean if it's continuous, I can take the derivative. We just showed the prime example, the easiest one, with the absolute value of x. We said the derivative does not exist at 0. Right here. We said the derivative does not exist right there. So that tells me that the converse of this is false, right? So if you can take the derivative, it for sure is continuous. But if it's continuous, that does not mean you can take the derivative. Here is continuous, but I can't take the derivative there. Okay? So here's when we can't differentiate something. Any graph that has a corner or a kink means it doesn't have a tangent at this point, right? I don't know what the tangent is at that point. Is the tangent this way or is it this way? The slope of the tangent, it's definitely not horizontal, okay? So we don't know if the slope of the tangent is negative, if it's positive, because it's definitely not horizontal. So there you go. We can't have a tangent at that point, so we can't take the derivative at a corner or kink. It doesn't matter if it's continuous. If it's continuous, it doesn't mean it's differentiable. But if it's differentiable, it does mean it's continuous. Here's another example of a kink. There's a kink right there. I can't take a derivative. Another situation, a discontinuity. I cannot take the derivative at a discontinuity. So in this example, here I have a discontinuity. I don't know where the tangent is. Is it here? Is it there? I can't do a tangent line. Because remember, the derivative is the slope of the tangent line. If I can't get the slope of the tangent line, I can't get the derivative. So anything that has a discontinuity, that means there is no derivative there. Any vertical tangent, right? What's a vertical tangent? It's undefined. There is no slope to it. It's undefined. So since the slope is undefined, I can't get it. I can't take a derivative there. All right, so with a graphing calculator, you got to zoom in at a point and see if it's vertical or not. And then you can determine differentiability. One example is on page 129 of your textbook. So be careful with graphing calculators because they don't always show you exactly what it is. Make sure you zoom in. All right, we can take higher derivatives. So we can take f double prime. So f prime and prime again. So this is the second derivative. We could take it multiple times. We could take the third derivative. One year they did this on the AP test. They did f to the fourth like that, in that notation. You could put it in parentheses. This just means fourth derivative. In fact, I could say f with an n here, and that gives me nth derivative. Okay, so whatever they put up here, it doesn't mean the function to the fourth power, the function to the fifth. You're taking the fourth derivative, the fifth derivative, the higher order derivative. Okay, now in Leibniz notation, we can say d squared y over dx squared, like that. Okay, that means a derivative with respect to x of this derivative, the derivative of y with respect to x. You could say d4y over dx to the fourth. This means fourth derivative. Okay, so you could take the derivative multiple times. Now, you don't want to have to do it the long way 4 times. We're going to get to a shortcut next section. All right. And let's take a look at these higher order derivatives. Okay, typically anything past the third order derivative, we just use numbers. In other words, f to the fourth means fourth derivative, and so this I just told you that I said. So look at over here. If you have the position function, if I take the derivative of a position function, I get the velocity function. So the derivative of a position gives me velocity, which should make sense, right? It's the instantaneous rate of change because you're finding that tangent line. Guess what happens when I take the derivative of the velocity? I get acceleration. So that means the second derivative of the position is the first derivative of the velocity, which yields an acceleration. Can you do it again? Sure. If you take the third derivative of position, you get the second derivative of velocity, which is the first derivative of acceleration, which we call the Mr. N function. No, we call it the jerk function. No, I'm not a jerk, but we call it the jerk function. We don't have anything past that as far as motion is concerned, okay? So remember, jerk function is like suddenly jerking something to get it that initial movement, right? Acceleration is as it gets going faster and faster and faster, but that jerk is that initial oomph to get it going. Okay, so let's do some examples now. Over here, we got to match the graph with its derivative. So I want you to pause the video at this time, and I want you to try to do these, and I'm going to give you the answers in a minute. So try to do these, and we'll talk about them. So let's take a look at this first one. This first one tells me that I have a kink at around this point. Kink means I can't take the derivative there. So I have to look at all these derivative graphs, and at this point in the x, I don't have a value there. I have to see right here, was I able to graph something here? Yes. Remember, at a derivative, you can't graph anything, right? It's a kink, so nothing there. Over here, that's not it. Over here, that's not it. Over here, that's not it. Over here, possibly. And over here, possibly. So it's possible D or F. Now let's take a look. This is linear. It's a linear slope and it's positive. So that means the derivative will be above the axis going this way. Okay? So let's change this tool. I want to show you something here. So that means it's going to go this way, right? This is a positive slope. I need to be above the axes, and from this point, it's going to go that way. This is a horizontal slope, so that means from here, it's a 0 slope. So I'll be 0 all along there. So it's got to be D. This is open circle that way, open circle at 0. So this first one must be D. Okay, the second one, look at all these kinks. Well, it's got to be this one, right? It stands out. So the second one is F, and that should be a capital F. Oops, I don't know what just happened. But that should be a capital F so that I don't get it confused with the other F. So let's fix that, make this a capital F here. So then this answer would be a capital F, okay? All right, so on the next one, all right, so this one might be a little confusing to you guys because look, over here, the slopes are almost horizontal, then they get increase, back to horizontal. Increase, and they got to decrease at some point, right? Increase, decrease to 0. So the slopes are pretty much 0, then they increase and go back to 0, okay? But then on this side, they're negative, so it changes from positive slopes to negative slopes at the axes. So I go from above the axes for the derivative to below the axes. And then these slopes go super small negatives, big negatives, back to super small negatives. So let's see, which of these matches up with that? So remember, I've already used D, I've already used F, so from what I have left, I need to find what goes horizontal, so horizontal, this is definitely not it, horizontal, and then increases, goes horizontal. Horizontal increases, but I need to be at 0. So, right, this is a horizontal tangent, this increase, but I need to be at 0. So that one is out. This one is out. The only one it can be is this one, because 0, increase slope, back to 0. Decrease slope, back up to 0. Remember, up to 0. Slope goes to 0, go up to 0. This is on negative side, that's negative. Besides, it couldn't be this one because these are negative slopes and all of this over here is above the axis. These are positive. I need negative values for the negative slopes. Remember, I'm graphing the slopes. The slopes have negative. When I graph a negative value, it's below the axes. So C must be B. All right, so now we've used this one. All right, for D, all right, let's take a look at D. Over here, we've got a horizontal tangent. So I'm going from almost horizontal slopes, so really small slopes, negative, to really large slopes, negative. All right, so now with these choices, what's left? I'm going from really small slopes, negative, so I'm below the axis, to really large slopes, negative, again, below the axes. On this side, it's kind of opposite. I go from really high positive slopes, right, which would be above the axis, to really high positive values to really small positive values. So it's got to be C. Oops. I keep choosing that wrong one. All right, so now I've used that one. All right, we got 2 left. Over here, take a look at this one. I'm going from positive slopes, really small, to almost like 1. Okay, really small to almost like 1. All right, so here we go, really small to almost like 1. Oh, it can't be this one. It's got to be A. And then on this side, let's verify. I got positive slopes again, so I'm still above the axis. All of these are above the positive slopes, positive slopes. All right, slopes of the tangents, positive, positive. Over here, I'm going about 1, back to 0. 1, back to 0. So this one must be A. And finally, well, that leaves us this one that has to be E, but let's verify it. Again, here I have a horizontal tangent, so that value is 0. 0. Over here, I've got negative slopes all the way to almost vertical. Negative slopes, so below the axis, almost vertical, so that's a huge number. Over here, positive slopes, again, almost to vertical, right? This tangent, look how steep that is, and that's what that's going to be, a really high positive number. So it is E. All right. on this one, let's take a look at these and see what we got. We have to sketch the derivative of each of these on this first one. Oops, I can't tell which is the axis, but I'm just going to base it on what I did here. So I'm assuming this is the axis, and right here we have a horizontal tangent. So what does that tell you? That means the derivative, everything is going to be 0. So this will look like that. It's all at 0. Okay, the derivative here, I'm just going to sketch it right on it. Well, if I take the sine of 30, I'll get negative 1, and it's a negative, right? It's negative slope. So I'll have, I'm sorry, negative 1/2, I should say. So at negative 1/2, I will have, and that's a kink right there. So I'll have an open circle going this way. Over here, negative slope, but it's 45 degrees. 45 degrees is the negative 1 version. So then I'll go like this. Over here, these are not supposed to be kinks. I'll tell you right now. These are supposed to be smooth. So smoothen those out. And when you smoothen these out, let's kind of draw it so it looks a little smoother. When you smoothen these out, you look for the horizontal tangent. Horizontal tangent right there, so that's a 0. Horizontal tangent, that's a 0. Horizontal tangent, that's a 0. Look at the slopes. The slopes are positive, the slopes are negative. So that means on this side, I'm above the axis, so I'll go like this. On this side, I'm below the axis. I'll go like that. Oh, look what I did here. Positive above the axis. But remember, positive increasing and then decreasing back to 0. Right? Any function that looks like this is going to increase super quick, but then go back to 0. Look at the slopes. They increase, right? Increase, and then they start to decrease back to 0. So typically, halfway, where that inflection point is, halfway, that'll reach that maximum. So right there, up and down, and then the rest will go like this. All right, over here, identify which is what. Well, remember what we said? The original is going to have the highest order. If I take a look at this, that's got to be, oops, I can't trace. That's got to be the f of x. Then I take a derivative, I take a curve out of it, right? That's got to be f prime of x, and then this would be the f double prime of x. All right, I've got more examples for you in class. I've got a whole other video on derivative sketching. A lot of times you guys find this extremely difficult at first, and then there's just that one thing that clicks, and then it makes derivative sketching super easy. So watch the other video. Hopefully that thing will click sooner than later. Thanks for watching, though. Be sure to leave a like and subscribe, and I'll see you guys in the next video.